In 2019, Google made a bold claim. Their quantum computer, Sycamore, had performed a calculation in just 200 seconds, something that would take the world's most powerful supercomputer 10,000 years. But the story doesn't end there. Today, a new contender is already here. Google Willow.
It grew from 10,000 years in 2019 to 10 to the power of 25 years, or in words, 10 septillion years on the Willow chip.
A calculation that takes Willow under 5 minutes would take the fastest supercomputer 10 to the 25 years.
Willow isn't just about speed or computational power. The device claims to harness the fabric of existence itself, tapping into parallel realities and calculating across multiple universes simultaneously.
People ask the question, how come quantum computers are so powerful? It's because they compute in parallel universes. This is the multiverse. The multiverse idea comes from quantum physics. Electrons can be two places at the same time.
If that holds true, then what are we really looking at? Could we be standing at the brink of a revolution that redefines reality as we know it? A portion of this video is inspired by a popular book, The Fabric of Reality, by David Deutsch. If you haven't heard of him, he's a physicist known for his groundbreaking work in quantum mechanics and the many worlds theory. A lot of his ideas challenge how we think about reality itself, making him one of the most influential thinkers in modern physics. Professor Deutsch explains that as the modern world progresses, we're faced with questions that classical physics simply couldn't answer. This is because everyday laws of physics like the motion of planets, cars, or even simple measurements break down when things get extremely small or extremely fast. At the atomic level, particles don't behave like tiny balls. They're fuzzy, unpredictable, and can be in multiple states at once. And at the same time, when the speed of objects gets extremely high, time and space start to bend. Classical physics couldn't handle this weirdness, and that's where modern physics stepped in. And so, this led to the development of quantum mechanics, a theory that describes the universe at the tiniest scales. It explores a world that doesn't match our everyday intuition. Take classical physics, for example. If you measure an object in a room, you expect to find it at a specific position, right? That's because classical physics follows clear and predictable laws. But at the quantum level, things don't behave that way. And so, many people have differing opinions on quantum mechanics. One of the most well-known debates is between the Copenhagen interpretation and the many worlds interpretation. Subatomic particles can exist in multiple places at once before being measured. And when they are measured, they suddenly choose a single location. This randomness is what the Copenhagen interpretation suggests, that before measurement, quantum systems exist in multiple possible states at once. But not everyone agrees. Professor David Deutsch, along with many other physicists, supports the many worlds interpretation. This idea suggests that all possibilities exist, just not in the same universe. Instead, every possible outcome happens, but in a separate, parallel universe. So when you measure a quantum particle, you're not collapsing reality, you're just seeing one of many realities unfold. Here's where Schrödinger's equation comes into play. It mathematically describes how quantum systems evolve over time. Instead of predicting a single outcome, it gives us a probability wave, a range of possibilities that only resolve when measured.
Erwin Schrödinger constructed an extremely interesting thought experiment. Cat is locked inside a steel chamber with a tiny amount of a radioactive substance, a Geiger counter, a vial of poison, and a hammer. As soon as a radioactive atom disintegrates inside the steel chamber, the Geiger counter triggers the release of the hammer, which smashes the vial of poison. The cat is dead. However, due to the wave characteristics of the quantum world, that atom is indeed disintegrated and intact. Both states are true until we view it in a definitive state of existence. Until the moment we check and see, we don't know if the cat's dead or still alive.
What the theory says is that the cat is in a superposition of these two states, and then you come and look at it and you're in a superposition of these two states.
But this debate leads to an even bigger question. Where do we draw the line between the quantum world and our everyday world? Sean Carroll, an American theoretical physicist, argues that we shouldn't separate them at all.
After all, you are a body made of a whole bunch of quantum mechanical particles, electrons and protons and neutrons.
So in other words, Humans are made of atoms, and atoms follow quantum rules. So if the microscopic world behaves in strange and probabilistic ways, doesn't that mean we too are part of that quantum reality? I mean, if atoms can exist in multiple states at once, why don't we see people existing in two places at once too? Why do we experience one reality and not many? The answer to that lies in quantum decoherence.
In the quantum world, we talk about quantum coherence leaking out into its environment. Another way of saying this is that it becomes entangled with its surroundings, entangled with its environment. So decoherence is a universal process. It happens all the time. You prepare a quantum state that starts off isolated from its environment, and inevitably it becomes entangled and decoheres its information into the environment in a one-way process.
This is why we don't see quantum effects in everyday life. Sure, humans are made of atoms, but we don't pop up in two places at once. The moment a quantum system interacts with its surroundings, it loses its quantum weirdness and starts behaving classically. But what if we could control that decoherence? What if we could keep quantum states stable long enough to actually use them? That brings us into the next topic of this discussion. Humans have always used tools to solve problems. Our hands can be used to count, to compute. Classical computers operate on a binary system, ones and zeros. They're fast, but they still follow classical rules, just like the physical world we see around us. Quantum computers, on the other hand, operate on quantum states. Instead of just ones and zeros, quantum bits or qubits exist in multiple states at once, which is called quantum superposition. This is what gives them their immense power to process vast amounts of information simultaneously. This is probably the most important graphic you need to see today. Quantum computing works by exploring many possible pathways at the same time. If you hit a dead end, you don't need to go back and try another route, like in the classical example. But a new version of you splits off to explore the different routes, all thanks to the quantum property of superposition. If all of this sounds like something out of a sci-fi movie, then you'd better be ready. We're about to show you tangible evidence that supports these ideas, just as Professor Deutsch himself has discussed.
When a quantum computer is built, a small quantum computer with a few thousand qubits, that's the quantum analog of bits. In other words, a very, very weak, comparatively weak quantum computer could perform more computations simultaneously than could be performed by the entire visible universe.
But where does that computational power truly come from? To begin answering that, we first need to take a step back and look at one of the most famous experiments in quantum physics, the double-slit experiment. Suppose you fire individual photons, like tiny flashlights, at a barrier with two slits. If photons were just particles, we'd expect them to go through one slit or the other, forming two distinct lines on the screen behind them, right? But that's not what happens. They create a strange pattern, a series of bright and shadow bands, as if each photon behaves like a wave. This is the famous double-slit result. Now let's take that even further. What kind of shadow do we get if we cut another pair of slits into the barrier, such that we have four slits like this? Common sense says the pattern should stay mostly the same, maybe twice as bright, a little more blurred. But no, that's not what happens at all. The real pattern looks like this. Clearly, the four-slit pattern isn't just two slit patterns stacked together. It's something new. Look at this spot right here. With two slits, it was bright, but with four, it went dark. So add two more light sources and the point goes dark. But if you remove them, it lights up again. Why is it? Something must be coming through the second pair of slits. What Professor Deutsch described in his book was nothing short of astonishing. He wrote, "When a photon passes through this setup, it goes through one slit, but something else interferes, deflecting it based on which other slits are open."
The conclusion that we draw is that this thing behaves like light in every way we can detect experimentally except one, and that is we can't detect it. It is there because it pushes aside the light that we can see.
For the sake of argument, call this thing a shadow particle. Different interference patterns emerge depending on which slits are cut, meaning shadow photons must be landing all over the screen whenever a real photon arrives. And so, there must be far more shadow photons than tangible ones. Professor Deutsch then elaborated that all these shadow particles, collectively, we might think of as a parallel universe, for they too are affected by tangible particles, but only through interference phenomena. So here's what happens. The subatomic particle of that particular photon has counterparts in other universes. It is through interference that the paths head toward the same point on the screen. Perhaps what we see in this universe is the inverse of what it would have been in another parallel universe, where the pattern would look something like this.
All particles behave like this, not just light, but even the particles in the screen, the particles that you and I are made of. They all are affected, shoved aside by counterparts of themselves that behave exactly like those particles but cannot be seen. They are real matter, real energy, real light that we cannot see, and so they are an entire parallel world of matter, energy, and light. That's why we called it a parallel universe, and there are many of them.
Now that we have established a pretty good foundation of the topic, let's look at some of the practical cases. The superposition of a qubit is written as the combination of two states. Now, what do you think you'll observe if you try to measure the state of this qubit? Is this a definite 1, or is it going to be 0? Obviously, in superposition, you might have the combination of those results. So, this is the right answer. Then when we have a qubit in the state like this, what do you think you'll observe? Well, just look at the probability here. Since 0.9% is higher than 0.1, common sense tells us that it's very likely you measure 1. And if you like interactive learning like this, I highly recommend checking out Brilliant.org. They have several courses on quantum computing made in collaboration with Microsoft and Alphabet X. It goes in-depth into the many hard problems of computing, with topics like superposition, quantum parallelism, and many more. The Brilliant app makes it super easy to learn anytime, anywhere, right on your phone. Whether you're diving into a new topic or just doing a quick practice session, you can level up your skills in just minutes a day. To try everything Brilliant has to offer free for a full 30 days, visit brilliant.org/beyondideas or scan the QR code on screen. You'll also get 20% off an annual subscription. That way you can learn the intricate details of quantum computing and how it fits into the bigger picture of our universe. Going back to our discussion that if we want to model our universe, we need a system that truly mirrors the natural phenomena we see around us. Just like what Richard Feynman said, nature isn't classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. We've already talked about how quantum computation differs from classical computation, but here's something even more profound. If we tried to match the power of a quantum computer using a classical supercomputer, we'd run into a fundamental problem: storage. A quantum system with n qubits can exist in 2 to the power of n states, meaning a classical computer would need 2 to the n classical bits just to keep up. So as qubits increase, the numbers quickly become astronomical. For example, a 50-qubit quantum computer already requires as much memory as about 1 petabyte in a classical system. By the time you reach 300 qubits, you would need more bits than the number of atoms in the entire observable universe. At that point, no classical supercomputer could ever keep up. Some quantum calculations are so complex that a classical computer wouldn't just run out of memory, but it would also need longer than the entire 13.8 billion year history of the universe to finish the task. And this brings us to another mind-bending topic. Where exactly does this insane computational speed come from?
People ask the question, how come quantum computers are so powerful? It's because they compute in parallel universes. This is the multiverse. The multiverse idea comes from quantum physics. Electrons can be 2 places at the same time.
This is the claim that physicist Michio Kaku once mentioned, that one possible explanation is that quantum computation doesn't just happen in our universe, it happens across multiple universes. And it turns out that David Deutsch also explores this idea in depth.
That's fascinating. I did not know that quantum computing was a byproduct of you attempting to create a test for multiverse theory. You find out that reality is capable of greater computation. And when you combine these theories, as you often do, I find that they're beautiful outputs. Like, for example, I think you mentioned that quantum computation can do things like Shor's algorithm, which factors prime numbers. This is a big problem in cryptography.
Composite numbers, yes.
Yes, it relies upon the fact that it's very hard to factor large complex numbers, but it's easy to combine them and so on.
Yes.
And where's a quantum computer getting the compute power from to do all this when a classical computer can't? And the Occam's razor answer just cuts through it. It's like, well, it's using the whole multiverse to do the computation. There aren't enough atoms or bits in our universe alone to do it.
And speaking of real-world quantum computing, let's take a look at Google's latest development like we've mentioned in the beginning of this video. Willow. This is Google's most advanced superconducting quantum chip to date. It's the next step in their mission to build large-scale quantum computers capable of solving problems that classical computers simply can't.
We've pitted Willow against one of the world's most powerful supercomputers with the random circuit sampling benchmark. The results are pretty surprising. By our best estimates, a calculation that takes Willow under 5 minutes would take the fastest supercomputer 10 to the 25 years. That's a 1 with 25 zeros following it, or a timescale way longer than the age of the universe. This result highlights the exponentially growing gap between classical and quantum computation for certain applications.
Think about it this way. If Sycamore made headlines for achieving quantum supremacy, then Willow is the next frontier. We're pretty sure that it'll push the boundaries even further.
It grew from 10,000 years in 2019 to 10 to the power of 25 years, or in words, 10 septillion years on the Willow chip. This illustrates the double exponential growth in compute power.
For centuries, we humans have used our hands to count. Classical computers, in their most basic form, use a binary system, but quantum computers, they operate on quantum states. And so if we apply the same logic we discussed earlier, then to fully calculate all possibilities, we would need more than just the observable particles in our universe. We would need an entirely new universe, or more accurately, a real multiverse. This concept connects us back to Schrödinger's equation. It describes how quantum states evolve over time. But this equation doesn't just describe a single possibility, it describes a superposition of possibilities, meaning that all possible outcomes must exist somewhere. And according to many worlds' interpretation, that somewhere is the multiverse itself.
It changed world history. We're not talking science fiction. We're talking fundamental physics of the universe.
Now that we've explored the scientific basis of quantum mechanics and the concept of parallel universes, it's time to ask a deeper question. If the multiverse is real, then what are the consequences? Can we somehow connect with these other universes? Or even travel between the two?
Every world, every possibility, at the same exact time.
Pop culture is filled with stories of people jumping from one universe to another, meeting alternate versions of themselves, rewriting history, or even escaping to a better reality. But is any of that actually possible? Professor Deutsch, once again, has addressed this question directly.
How do I know in which universe I am? Or how do I even know who I am, what I am, if there are multiple copies of me?
The thing is, the fact of the matter is, there are two of you, and they are identical, or they were identical, until they started to become different by having different things happen to them. And it's the same with you and your counterparts in other universes.
Sean Carroll also mentioned the following commentary.
So are they me, just in a different universe, or are they a separate person? I think the clear answer here is there's a relationship, but they're a different person. It's very much like identical twin. You have one fertilized egg. There's at one point in time a single cell that is one identity, right? One entity there in the universe, but it splits into two different people. I think that's how we should think about different versions of ourselves in the multiverse.
It's safe to say that the idea of physically moving from one universe to another is pure fiction. There's no known physical mechanism to make it possible. And if there are countless copies of you in different universes, it wouldn't make sense for you to jump between them. These universes may exist, but they're not like parallel highways where you can switch lanes whenever you want. So I hope that clears the air a bit. An important question you might be thinking at this point. Well, if we can't travel between universes, do they interact at all? Remember the double slit experiment, right? Where a single particle seems to interfere with itself, as if it traveled through both paths at the same time. So in the same way, universes don't communicate directly, but under the right conditions, they influence each other through quantum interference. And so if every quantum event splits reality into multiple outcomes, then in some way, all possibilities are real. There exists a version of you that made a different choice. But these versions will never cross paths. They evolve separately, dictated by their own chain of quantum events. So while we can't send messages to another version of ourselves, the choices we make and the measurements we take do play a role in shaping which version of reality we experience. From a philosophical standpoint, the multiverse idea reshapes concepts like determinism and free will. Some argue that free will still exists because in each individual universe, we experience the consequences of our decisions, as if they were the only reality. Others suggest that everything that can happen does happen, and so free will is just an illusion, a matter of perspective. But beyond philosophy, there's a practical aspect. Understanding quantum interference has real-world applications in computing and even the future of artificial intelligence. If quantum computers harness interference effects between parallel universes, then in some way, the multiverse is already being used, just not in the way sci-fi movies imagine. So while we may never step into an alternate universe or meet another version of ourselves, the influence of these parallel worlds is very real. And as our understanding of quantum mechanics deepens, who knows what new questions we'll uncover? The mysteries of the universe are far from over.